All right, then our last information here out of this chapter then is concerning a couple of just a bit of a hodgepodge of things that we haven't talked about yet that we need to. So one of the things that gets mentioned when we start talking about unit cells, especially when we start talking about blending unit cells or blending different atoms into a unit cell, is, well, how does the thing that we are adding fit in to the existing cell structure? And when we answer that question, the type of whole that is being discussed is usually what is ultimately being asked here. And so there are three primary types of holes in a lattice structure. The first is the cubic hole. Now, we've already seen the cubic hole in use. This is basically what happens when we have body center unit cells. The second layer fit in the cubic holes. With a cubic hole, we get a coordination number of 8, where that atom that is being put into the cubic hole is going to be touching 8 others. The second type of hole that we talk about often is something called an octahedral hole. Now, this is where our discussions going back to, especially with these last two. What does octahedral mean? What does tetrahedral mean? We got to kind of go back to those molecular shapes concept that we saw in Chem 105. An octahedral hole is basically if we put a new atom in the octahedral position. So if you remember what that looked like, it was three-dimensional shape. The center atom had 4 that were touching it in a plane and 2 that were touching it above and below in an axis. That's how we get 6 for its coordination number here. Where we can see this kind of thing happening a lot more, take a look at this face-centered kind of design here. Atoms that exist in between the faces of a cube can have octahedral holes there. And then the third type of hole is something called a tetrahedral hole. Now, we haven't talked a whole lot about these kinds of atoms or these kinds of unit cells that only possess half of the unit cell's corners. But that's basically what's happening here. You can see that we have a unit cell that is setting up a tetrahedron here. So if you remember from that geometry, that was steric number 4, 109.5 degree bond angles. And so that's the kind of hole that is generated here. And so just to give us a couple of examples of what that kind of looks like. So the cesium chloride structure, for example. What we see in cesium chloride is we've got an array mixture here. The cesium atoms occupying what look like simple cubic cells. And then you've got these chloride ions that are sitting in the octahedral holes. And if we put them together, it looks like a body-centered cubic kind of arrangement, where the corners are the cesiums and the bodies are the chlorides. In tetrahedral, we see something like this. This is called zinc blend. And in the zinc blend structure, what we can see is that we've got sulfur forming this tetrahedral kind of array. So it looks like a full-on unit cell. But we can see that with these zinc sitting in the holes, we've got a very interesting combination here. The sulfur is in a face-centered kind of an arrangement. And so we've got 4 sulfurs per unit cell. And then the zinc that are caught in between are all inside the body of the unit cell. So we've got 4 zinc caught in the unit cell. And so the actual ratio of zinc to sulfur here is actually just 1:1. And then with sodium chloride, again, we're getting octahedral holes here. This is a lot more of a complicated one because sodium and chloride there's not nearly as big of a difference in size between them compared to something like cesium and chlorine. But again, we get octahedral holes being used up here, where we can see that if I look closely, so I'm just going to pick on this chlorine right here. I can see that this chlorine is touching this sodium here. So that's 1 and 2 and 3 and 4. So that's the 2-dimensional plane. And then in the axis positions, there's 1 down here, and then there'd be presumably another one up here to give us the 6 for that octahedral spot. So with the cesium, we get the cubic structure, which kind of resembles body center. With the sodium chloride, we see a different kind. We see something that's more face-centered looking, but all of those different octahedral holes being exhibited. And then we see the tetrahedral holes in the zinc blend. And we'll come back to this. We'll start looking at other crystalline structures and trying to identify what kind of holes are being utilized there, and can we evaluate the empirical formula based off of this these drawings. But I want to switch up real quick here and talk a little bit about something called band theory. Now, we're not going to get too deep into the weeds here with band theory. First of all, we really didn't talk about molecular orbital theory at all in the past. But what I want you to think about is molecular orbital theory is basically just an extension and an overgrowth of atomic orbitals. And what I want you to think about from that standpoint then is if we take a large sample of a particular substance, like say sodium, what we'll notice is that the occupied electron orbitals inside of sodium are going to form this valence band down here in purple that represent the atomic orbitals, the orbitals that have electrons in them. So the purple orbitals here are ones that are filled up. The red ones here are ones that are partially filled. So like the ones here in this valence, the sodium band here. So our electron configuration for sodium is neon 3s1. So the occupied orbitals from the core electrons come down here. The valence electrons are here in this valence band. And so what band theory tells us is that the reason that a metal can conduct electricity is that there is no gap in its bands. So the valence band and the occupied band here, those are full of electrons. And even though there are lots of empty orbitals inside of sodium or any other metal, the fact that the band that is empty overlaps with the band that is at least partially full means that electrons are able to travel from one band to the other. And since they can travel from one band to the other, that's what allows electricity to flow inside of the atom or inside of this metal sample. So the empty conduction band has to overlap with the occupied band if we're going to see electrons flowing through the metallic sample. And the reason for this is because if those orbital bands overlap, then that means that electrons can travel from the open band to the unopened band, the occupied to the unoccupied, relatively easily and conduct electricity very, very well because the electrons are free to move all throughout the metal sample. Now, I don't have a picture of this, but if we can imagine what a non-conductor looks like, what we would see is that something that does not conduct electricity would have a far energy gap to overcome between the orbitals that are occupied with electrons and the orbitals that don't have any electrons in them. So if there were a gap between them, if there was not overlap, then what we would have is a non-conductor. Semiconductors, on the other hand, what we see with semiconductors is that there is just enough that there is a band gap, but the band gap is small enough that if we introduce material to it, the material can actually help to bridge that gap and make it so that the material is able to conduct electricity at least a little bit. So by definition, a semiconductor is a material that has an electrical conductivity between that of what we expect out of a metal, highly conductive, and what we expect out of a non-metal, not conductive. And further, we can increase its conductivity by introducing chemical factors that would help to do so. Those chemical factors come in two types: the N-type semiconductor and the P-type semiconductor. What's the difference between the two? Well, an N-type semiconductor is doctored by adding an electron-rich substance. Why does that matter? Well, more electrons being present is going to raise the valence band. Since the valence band is being raised, the band gap gets lower, and we have a greater mobility of electrons. A p-type semiconductor contains something that is electron poor, and what this does is this lowers the conduction gap, the conduction band, making the gap smaller. So the whole point of a semiconducting, of doping a semiconductor with some sort of extra substance, is to artificially make the band gap smaller. And so if the band gap is already kind of on the smaller side, and we add a semiconductor to it, it makes the whole thing smaller still, making the increased likelihood of getting electrical conductivity. So here are a couple of examples of how that might work. So let's take the most commonly known semiconductor, silicon. Silicon has between its valence band and conduction band a band gap. And so this band gap on its own makes silicon kind of difficult to conduct electricity on its own. Here's where the extra kind of conductors come in. So for example, if I add an N-type semiconductor, like phosphorus, phosphorus has extra electrons. It has one more electron than silicon does. What this does is this will raise the valence band from here up to here. Now that band gap's not nearly as prominent. Electrons are able to flow at least moderately from the silicon to through the silicon sample. So that's how an N-type works. How a P-type works, gallium has fewer electrons. And so what it does is it's going to move the acceptor gap down closer to the valence band, and it's going to shrink the gap that way. And because the valence gap is now shrunk in that direction again, it's a lot easier for the electrons to flow through the sample of silicon because their conduction band is a lot closer to their valence band now. Now, the question you might have is, well, what if you do both? Well, if you do both, then you've got yourself on the makings of a diode. Diodes use N and P junctions to conduct electricity. You've heard of diodes, in particular those that emit light. Light-emitting diodes, LEDs, have been on the market and in prominent use now for over a decade. But this is basically how semiconductors work. Is semiconductors work on the principle that if we add a small amount, and again, we're not completely flooding the silicon with phosphorus or completely flooding it with gallium, but introducing a small amount into the structure of the silicon is enough to get that conduction gap to shrink and make electricity at least a little bit easier to flow. All right, let's come back to ionic solids then. So ionic solids are going to represent very similar kinds of structures to what we described with metals. We're going to see simple cubic, we're going to see body-centered, we're going to see face-centered. Now we're going to see probably a couple of other things as well. But what we're really going to be looking for here are a couple of things. One, coordination number. If I look at this lattice, how many atoms, how many ions are they touching? And coordination number is largely going to be dictated by, well, what kind of hole are they occupying? Are they occupying a cubic hole? Are they occupying a octahedral hole? Are they occupying a tetrahedral hole? Now, the array that gets formed in the first place usually is going to have kind of a structural start. And that structural start is going to resemble one of our types of lattices. And it's usually going to be anions that represent that lattice. And the reason why is that anions are usually larger than cations. Not always the case, but usually speaking, it is. And so we usually find the corners and sometimes the faces or the bodies occupied by anions, and then cations trying to fit into the holes. So here's our first structure. Cesium chloride. Now we can see that cesium chloride, we have the chloride ions set up in a simple cubic arrangement. All we have are the chlorides on each corner of the atom. The cesium is sitting in between all of them. Based on what we talked about at the beginning of this, we can realize that this is a cubic hole. Since it's a cubic hole, the coordination number is 8. And the chemical formula, well, this is where we break it down. Chloride is simple cubic, so 1 chlorine. The cesium is sitting in the middle in the body, so 1 cesium. The relationship between them is 1 to 1. Empirical formula here is 1 to 1. Cesium chloride, CsCl. Now, mind you, these are ionic compounds. We would expect, based on charges, that cesium chloride is in fact 1 to 1 because cesium is a positive 1 and chloride's a negative 1. But now we can see that that also fits into it in terms of its structure as well. Let's take a look at another one. Well, let's take a look at this one. Here we have a sodium chloride cell. The green are the chlorides, the blue are the sodiums. So here's what I want you to do. Let's look at the chloride first. What kind of structure are the chlorides forming here? Is it simple, body-centered, or face-centered? Yeah, it's face centered. I can see I've got a chlorine on each corner, and then I've got a chlorine in between each face. So how many chlorides are in this structure? If it's face centered, 4. Now for the sodiums here, it's a little bit more complex. We didn't talk about edges, but let's try to rationalize it. If an atom were on the edge, because it's sitting here in these octahedral holes. If it's on the edge, how many other atoms or how many other unit cells are sharing that atom? Gabe, you said 4. Why 4? Yeah, so what you have to think about in this case is, again, if we're talking about something in the middle of the edge, let's kind of play it out the whole way. If I were putting together a series of dice, I press them together into a larger box. So something on this edge is going to be shared by this dice and this dice. But it'd also be shared by the one on top of each of them as well. So the edges are shared 4 ways. How many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 edges divided by 4 shares, that's 3. But we can't forget about this one that's stuck right here in the middle as well. That one's not on an edge, that one's in the body. So 3 from the edges, 1 from the body is 4 for sodium. I had 4 from sodium, 4 from chloride. Break that down. What is the empirical formula? It's 4 and 4. In simple terms, that's the same as 1 to 1. So the question is, how many sodium ions are present in 1 unit cell? Well, we just counted. It's 4 chloride and 4 sodium. And that breaks down to 1 to 1. And so that's represented here. This is the rock salt structure. Again, chlorides are in a face-centered cubic arrangement. So we have 4 chlorides per cell. The sodiums are occupying the octahedral holes. And so we have 1 in the center of the cell and 12 on the edges. So 4 sodiums per cell. So 4 and 4 is the same as 1 and 1. This is how we come up with sodium chloride as NaCl. Again, based on charges, that's exactly what we would expect. But now we have the unit data that verifies that. It is 1 to 1. Here's zinc blend again. In zinc blend, we see the tetrahedral holes being utilized by the zinc. So the sulfides here are in a face-centered arrangement. Face-centered would give us 4 sulfide per cell. Each of these zinc are in a tetrahedral hole, so their coordination number is 4. For zinc per cell. And so again, 4 to 4 is the same as 1 to 1. Our empirical formula is ZNS. Now this structure, this is the fluorite structure. It looks very similar. Very, very similar to what we just saw. This is a tetrahedral arrangement as well. The difference between the fluorite structure and the zinc blend structure is this. Inside of a unit cell that is face-centered, there are 8 tetrahedral holes. Zinc blend is only using half of them. In fluorite, all of them are being used. And so this is an interesting situation where here we have, instead of the cation making the face-centered arrangement, this time let me reverse that. Here we have calcium making the unit cell instead of fluoride. Now, the main reason this is happening is because the calcium is on the larger side compared to, say, sodium and others, and so it's able to hold that structure a little bit better. But what we can see is that the arrangement here, with calcium being face-centered, we're going to get 4 calciums per cell. With fluoride taking up all 8 of the tetrahedral holes, we're going to get 8 fluorides per cell. 4 to 8 is a 1 to 2 ratio. And so this is how we get the calcium fluoride is CaF2. Now, the fluorite structure does have an analog. It's called the antifluorite structure. And where we see that is when the situation is reversed. So, like lithium sulfide, for example, Li2S. We would have the antifluorite structure in that case. Sulfides would make up the lattice. Lithiums would fit into the holes. All right. Last thing that we'll talk about here are some network covalent solvent or network covalent solids. We're going to focus mostly on carbon because it's the most interesting. And we need to talk about what an allotrope is. So allotropes are just different molecular structures for a given element. We talked about this a little bit yesterday when we made mention of the idea of carbon versus graphite, diamond versus graphite. those are two different allotropes. It's the same structural stuff. It's all carbon. But the way that the bonds have arranged themselves is different and has created what seem to be different substances. Diamond is extremely hard. Graphite is extremely not. Diamond will not conduct electricity. Graphite does. What's the difference between them? Well, in diamond, we have a network covalent solid. And what we see is that every single atom is bonded to four others. So we've got this large network of sp3 hybridized carbons that are all attached to each other. And because of that, we get hardness, we get lack of conductivity because there's nowhere for the electrons to move because they're all in bonds. And we get high melting point because of the high level of attraction. Everything's bonded together. In graphite, what we see is this array of sheets of these planar molecules where we've got these six-membered rings that are bonded together. We can see that each carbon is bonded to three others covalently. And that what is holding these sheets together is basically intermolecular forces. Because those sheets are able to move over each other pretty easily, this is what gives graphite that kind of feeling that is of slickness, which is what allows graphite to be used in terms of lubrication for like machining or industrial kinds of purposes. If we take out the sheets part and talk about just sheet in the singular, what we have is something called graphene. Graphene has amazing tensile strength. It can be super thin, yet super strong. Fullerenes, or buckyballs as they are sometimes referred to, are a really interesting network array of basically carbon forming a soccer ball kind of formation. So what you see is that you have a 5-membered carbon ring here surrounded by a series of 6-membered carbon rings, very similar to the white and black patches on a soccer ball. Fullerenes can be very large, forming up to 60, 70, or even more carbon atoms in this soccer ball pattern. They were originally discovered in the 1980s and found in soot, but they became kind of a foot in the door for nanotechnology. If you look at the footprint here, this soccer ball arrangement is roughly 1 nanometer in diameter. And so a lot of different kinds of things have been done with drug delivery or other kinds of things trying to trap molecules inside of this cage to deliver them to from one zone to another, one part of your body to another. This is where the earliest stages of nanotech were going. And they eventually developed into things like these nanotubes, where we take that graphite sheet structure, we roll it out into these tubes. Again, the diameter of the tube is in the 1 to 2 nanometer range. And we get some semiconducting behavior out of it because of the way that the arrangement of the electrons is there. We also get extreme strength out of these nanotubes. In phosphorus, we see some of the same kinds of things, although not to nearly the level of complexity or variability. But we do see that, for white phosphorus, what we have is a four-membered, a tetrahedral, basically, where all four atoms of phosphorus are bonded to each other. So if you think about the arrangement of phosphorus in terms of its valence structure, what we see is that each of the four atoms in phosphorus bonds to the other three using these unpaired electrons that they have with each other. When we break out of white phosphorus, because that particular arrangement is not terribly stable, white phosphorus is water stable, but not air stable, reacts almost instantly with the air. With red phosphorus, what we see is we go to more of a ringed structure, where those four-membered rings are covalently bound to each other and create a network solid. And that increases their stability considerably. But there's also a third version, kind of where we go in between smaller and larger, called cluster. And that's kind of an in-between state. And so that is it for our discussions here in chapter 18. Before we go off for the weekend, are there any questions, anything that we need to go over? Okay, so one last point here to be earned, and then we will call it a weekend.